This conference will now be recorded.
Very good evening, students. We were discussing numerical problems on capacitance and capacitor chapter. So today we have picked up few very interesting and important numerical problems which are being asked in various competitive exam, basically NEET and JEE advanced questions, main and advanced. So we'll learn few very interesting concept over here, and those concepts can be utilized to solve numerical problems on capacitor. So as you can see, we have a circuit over here. So see, there are 1 2 3 4 5 6 capacitors are there, and each of them has identical capacitance C. So I have to find out equivalent capacitance between A and B point. So how to find out equivalent capacitance? We know series, parallel, etc. Series circuit or series combination. Okay. Then we know parallel combination. Right. These are all we know. So if we are given directly series or parallel combination, or if we can understand directly parallel and series combination, then we can use the formula we know. For series, you can write C1 C2 divided by C1 plus C2. For parallel, you can write equivalent capacitance C1 plus C2 if we have two capacitors. Okay. But in certain cases, you will not be able to understand directly whether some capacitors are in series or parallel combinations. We cannot understand just by looking whether they some are parallel or some are in series. So in that case, like this is one of such problem. See, you cannot directly understand which one is in series and which one is in parallel combination. So in this kind of concept, problems, we need to understand, or we need to learn a new concept. See, first of all, see, these are capacitors. See, this is one. This is another one. Okay, there are 6 like that. Okay, but you can see this is a conducting wire. This is actually conducting wire. Conducting wire. So whenever some part, suppose I have some general circuit like that, some general circuit, and some part of it is connected by a conducting wire. That means what? That means this is actually shunted in the sense, this point, see, if I just connect like this, so I am just making this, suppose there was potential here V1, so this point also I'm making V1, so kind of that. So what I'm trying to say is that whenever we are connecting this kind of conducting wire, we have to actually follow a tricks. Suppose I say A and C, A is connected to, or A, like A point has potential V1. So this is a conducting wire, this is going up to here. So that means this plate will be at potential V1, just this plate. Okay, I'm just writing here. So the first plate is at V1 potential, and second one obviously will be at some other potential. Let me take this as V2. Now look, this guy, this conducting wire is taking some potential through this and connecting here. That means this plate, the second plate, is at potential V1. Okay, because this conducting wire does not drop any potential, so wherever it connects, it takes the same potential and connect it. So this plate, this second plate, this plate will be at V1 potential. Now look, this is conducting wire, this is all the way going up to here, so this will be at potential V2. Okay, now see, this is V1 at V1, and see, this is all the way going, see, these are conducting wires, so no drop will be there, so this plate will be again at V1. But look, this is at V2, this point is at V2 all the way here to here. So this plate is also at V2, this is also V2, so this, all the points here will be at V2, and this wire, this conducting wire, is going and connecting over here. So what is the potential, or what is, at what potential is this plate is? It is at V2 potential. Okay, this is at V2. I hope you are understanding, because conducting wire, wherever conducting wire is connected, it is actually making the same point with the same potential. This is called same potential method. Same potential method. This method is called same potential method. Okay, this is called same potential method. Now look, so this plate will be then at same potential V2, but this will be at some other potential. Let us take this as V3. All right, now see, this V2 is connected here up to here, but this guy is already at V3, this plate. Okay, because in between these two plates only conducting wire is there, so this will be at V3, but this will be again at V2, and this V2 will be continuing up to here, V2, but this plate is at V4 and some other potential. I'm just taking V4. I'll just recap what I have done here. See, I have just taken this A point to be at V1 potential. So this plate, the first plate of this first capacitor, will be at V1 potential, right? But V2 will not be at the same potential, so I'm taking that as V2 potential. Now this conducting wire is going up to here, so this plate will be at V1 potential. On the other hand, so this potential V2 will be acting here, so this plate will be at V2. Now look, this will be continuing with V1 potential. Again, this is connected here, so this will be at V2 potential. Further, so this V2 is going up to here, so this plate will be at V2 potential, this one. Okay, and the second, see, this plate here is not connected to any other place, so this will be at some other potential. I'm taking that as V3, and this V3 will be continuing up to here, so this is V3, so this plate also will be at V3, but see, this V2 is connected again here, so this is at V2 potential. And see, this is V2 means this is also V2, but this is at, again, the last plate of the last capacitor will be at different potential. I have taken that as V4. Now look, to solve this problem, you know what you have to do? You have to make a table. What is the table? Potential difference, I'm just writing in short, PD, and capacitance. I mean to say, see, I'm just writing. Let us say this is V1 minus V2. There is one potential difference. I'll see how many capacitors are there with that same potential difference. See, this is one, this is another one, and this is another one. So I have three capacitors. So when I have capacitors, with same potential difference, I have to take them in parallel combination, right? So C, C, and C. Okay, three capacitors are there, and see what is the potential difference across them, V1 minus V2. So I have equivalent capacitance. Let me write this as equivalent capacitance. Equivalent. So equivalent capacitance will be here 3C with this potential difference, right? Now if I write V2, V3 with this potential difference, look how many are there. So this is one. I'm just erasing. Oh, sorry. Let me clean this portion. Okay. So yes. Now with V2, V3, this is one. Another one is this one. So I have two. So I'll be having two C equivalent capacitance. So I'm just erasing this also. So I have V2, V4, V2, V4. This is another C. Okay. V2, V4, another C. Look, then this whole thing, let me write once again. This is V1, this is V2, this is V2, this is V1. Again, this is V1, this is V2, this is V2, V3, this is V3, this is V2 again, like this. Okay. So let me draw an equivalent circuit for this. Equivalent circuit diagram for this. So I can just draw point A here. Some 3C equivalent capacitance. Okay. So they have, say, V1, V2 here, right? Then see what we have, V2, V3 and V2, V3 and V2, V4. Okay, V2, V3 and V2, V4. Okay, so that we have to see here. So V2, V3 and V2, V4. So look here, V2, V3. I have how much? With 2C. So this is one terminal. Another terminal will be V2, V4 with only C. This goes up to B. V2, V4. Look, why I'm writing this? Because I have, see, I have V1, V2, 3 of them. V2, V3, 2 of them. And see, they are actually not directly connected to B. They are not directly connected to B. You look this two things. So these are 2C, see V2, V3, right? V2 minus V3. So I'm writing here. So this is V2. So V2 minus V3 from here. There will be two parallel branch. V2, V3. But see, these are not directly connected. See, this branch is actually not going to B, right? This is not going to B. I have to calculate. I have to calculate equivalent capacitance between. I'm writing. We have to. This is only C. We have to calculate equivalent capacitance between A and C. Sorry, A and B. A and B points, right? But see, this branch is not going to B, right? This branch is not going to B. So I can ignore this 2C. Okay, so I can ignore this 2C. So this is 2C. So now ultimately what we have, this also will give me an equivalent circuit between A and B. This is this and this is this. So this is 3C, V1, V2, and this is V2, V4 between that. Okay, this is C alone. So these are in series. So these are in series. So in series combination, what will be the equivalent capacitance? Then it will be, see, this will be multiplication 3c into c divided by 3c plus c. So this will be actually 3c square divided by 4c. So it will be 3c by 4. So this will be the equivalent capacitance. Okay. I hope you have understood this. We'll just apply this knowledge. So this is the concept. So I'll just recap what I have done. We have to actually first of all we have to give the potential to each of them, each plate, according to the connection given. Okay, according to the connection given. Then we have to make a table like this. Okay, this two table like potential difference and equivalent capacitance, and we'll see the capacitors with same potential difference will be in parallel. So we have to write that, and other things will be in series actually. Okay, so we have to then draw according to that table, like according to the table we have to draw the equivalent capacitor, like equivalent circuit, and then we have to find out the equivalent capacitance. Okay, so this was the summary of the concept we have learned. Now we'll just apply this knowledge. Okay, let us take this numerical problem. So I have to find out same thing, like equivalent capacitance between A and B. So see, I have how many capacitors here? I have 5 capacitors here. So similar thing we'll do here. Look, this is B at B1. So this plate will be at B1, and this is some other potential. I'm taking that B2, and then see, this is going up to here. So this is at B2 again, but this is at B1. Okay, because this is connected here. Okay, so this is at B1 again. Okay, this is B1. So since it is at V1, and this is, see, this part is going and connecting here, this is at V2. Now look, this part, so this is going up to here. See, this is, see, this V2 is going here also here. So this plate is V2 at V2, and this plate is also at V2. What about this plate? So this V2, same V2 is going and connecting here. So this plate also will be at V2. Okay, and this plate will be at V2, and this is V3. Okay, so what I can write, look, potential difference and equivalent capacitance. So I'll just write here V1 goes here up to here, V1. This is with V2, it goes up to here, and this goes up to here, like that. Okay, see, with V1 minus V2, how many are there? This is 1, this is 2, and this is 3. So I have 3C here also. With V2 and V3, how many are there? V3 difference, potential difference between V2 and V3. I have only one. I have only one, this one. Okay, but what about this one? This, see, both the potential, see, both the plates are at the same potential. That means they will not store. This will not store any charge. Store any charge. So capacitance will be 0. We have to take capacitance 0 for this. So we don't have to consider this one. Okay, and other things are all in series. Look how. So this is 3C from A all the way here. 3C. This is V1, V2, and then this is V2, and this is V3 at V3. This is V. So these are all in series actually. Okay, these are in series. Okay, so in series means equivalent capacitance will be multiplication 3C into C divided by 3C plus C. So this will be also 3 by 4 C. Okay, so this is how we have to apply this knowledge. Okay, now I have another problem here. So here you can actually apply the knowledge somewhat here. See, I have, see, suppose this is V1 at V1, but here you know this will be at V1 fine, this also will be at V1 fine, but this will be at different potential. So let us say this is V2. Okay, this is at V2. So same V2 will be coming here and here also, right? If I say this plate is at V3, this plate is at V3, then same, see, these are all connecting wires, so this also will be at V3 and this also will be at V3. Then look, potential difference and equivalent capacitance. Equivalent capacitance. See here, I'll write V1 minus V2, V1 minus V2. So how many are there? So this is 1, right? V1 minus V2, right? All right. So I have only 1. So V2 my V1 minus V3. V1 minus V3, I have 1. So this is 1. What about V2 minus V3? V2 minus V3. So V2 minus V3, you look, V2 minus V3, I have 2, 1 and 2. So I have 2C here, right? Now we have to draw equivalent capacity circuit for from this table. Okay, see, I have V1, V2, all right. Then I have V2, V3. So this is V1, V2, V2, V3. But I have another one, that is V1 and V3. V1, V3. So this is so simple circuit, right? So this point is A and this point is B. I have to calculate the equivalent capacitance for between A and B. So V1 and V2 I have only capacitance 1. V1 and V3 also I have only 1C, and V2, V3 I have 2C. So these two are in series. This is in parallel. So series means, so let us say first take this one, C prime equivalent capacitance for this series. So 2C square divided by 3C. So CC goes off. So 2 by 3 C. Now equivalent, total equivalent capacitance will be, so this whole thing is now replaced by, let me draw another circuit. So the whole thing is replaced by C prime now, and along with that this C between A and B. Okay, so what is the equivalent capacitance now? So this will be C equivalent is equal to, in parallel, right? So 2 by 3 C plus C. So this will give you 5 by 3 C. So this is the equivalent capacitance. Okay, so this is how we will apply the same potential method. Same potential method. So far we have learned same potential method. Same potential method. All right. So let me go to the last problem. This is the last problem we will discuss today. See, this is also very interesting problem, and you have to find out equivalent capacitance between these two points A and B. Actually, this is really a tricky problem, and see, when we cannot apply all other methods, like same potential method, etc., when we cannot apply, then we have to apply a general method. So what we are going to learn now is the general method, and this general method can be applied anywhere and everywhere. Okay, so what is the general method actually? See, I can just think that this A point is connected to some positive potential, and B is connected to some negative potential of a battery. Okay, like this. All right, now what happens? The battery will actually send some charge. Let me say this is Q, and the whole charge will be actually divided into two parts, Q1 and Q2, kind of that. Okay, this way there will be Q1 and this will be Q2, because these are two parallel paths, at least up to this we can say, isn't it? One more thing is that this is kind of a Wheatstone bridge. Okay, this is kind of a Wheatstone bridge. This has symmetry of Wheatstone bridge. Okay, so we have, these are tricky problems, so you should sometime remember seeing the symmetry. Okay, so you can see there are four resistors like this. Okay, so and in between this is 2C, so this is unbalanced Wheatstone bridge actually, unbalanced, balanced Wheatstone bridge. Okay, this has symmetry, unbalanced Wheatstone bridge. All right, so I can say this Q2 is here, so Q2 charge by symmetry we can say Q2 charge is stored here also. Okay, so both are these are positive potential, and obviously this has to be negative then, right? So this also has to be at negative potential. Similarly, this will be at negative potential, this will be at positive potential, obviously. I'm sorry, this is just opposite way. Since this is negative, so this positive potential, otherwise there will be no flow of charge. Okay, so this is negative potential. Okay, again this will be at positive potential, and this will be at negative potential because it is directly negative here also, this is positive here. Okay, so by symmetry of the circuit we can say this is, if it is Q1, then this will actually store Q1, this is Q2, right? So this is Q2. Why I'm saying that? Because at balance condition, so if it is a balance one, then there will be no charge flow through this, but here it is now unbalanced one. Okay, so unbalanced one, so that's why we have to write this. Okay, so I'm taking this as some Q3 charge. Okay, Q3 charge. Okay, so charge is distributed, so this is called actually distribution law. Okay, distribution law according to Kirchhoff's charge conservation, or KCL, kind of KCL here we are applying. Now after doing this, I can actually see, I can write, see if I can find out the potential drop across each, like each loop, or you can say like across this, if you can find out the total potential, like Q by C, right? Q by C is V. If I can find out the potential drop across H, then we can write C equivalent, so total charge, because we know Q1, Q2, Q1 plus, according to our circuit, Q1 plus Q2 will be Q. So total Q by C equivalent will be exactly equal to the V1 plus V2 plus V3, whatever potential drop we get. Okay, so that is we are going to do now. Let me just erase this part first. See it here. See, as you know, the total charge will be Q is equal to Q1 plus Q2. That is for sure. All right, because this is the distribution we have got from total charge. Now look what we are doing here. Applying KVL. Applying KVL. KVL. So if I apply KVL, see, if I apply KVL here to this, maybe, so what we get, see, first of all, this one, actually what we are trying to do, you can see here, see, let me first write, so minus Q1 by C, then plus Q by 2C, and this is, sorry, Q2 by 2C, and this is okay. Let me just take one. So I'm going like this. If we go like this, so this will be negative side. We are just coming out from negative, so this is negative. But this is also negative, whereas this will be positive. Fine. So I'm just taking this loop. This is L1. So look, this also will be negative. 2C by, I'm sorry, Q3 by 2C. Q3 by 2C. This is equal to 0. Okay, this is equal to 0. Now we can just do a little bit of simplification here. I hope you are understanding. This is the loop 1 I have taken. So see, when current is or charge is coming out from the negative plate, so that charge has to be taken, or that potential has to be taken negative. So here also we have taken the same thing. This potential as negative. Okay, potential across this is negative, but here see, charge is going out from positive plate, so it is positive. Okay, Q2 by C2, this is positive, right? All right, so we'll just do a little bit of simplification. So this will be, see, this will be Q2 minus Q3 minus 2Q1 is equal to 0. If we multiply, like do LCM also, fine. So this is equation number 1, say. Oh, sorry, this is equation number 2. This is equation number 1. Okay, I hope you are understanding this. All right, so once again, you can see one thing here. See this dotted line. Plates inside the dotted line form an isolated system. How is it so? Because they are actually not connected to the other part of the circuit. Look, this is conducting wire, this is one another conducting wire, this is another conducting wire. So they are actually kind of making an isolated system. Okay, making an isolated system. Isolated system. So if they are making an isolated system, then I can say, see, I can say from here this concept, if they are making an isolated system, then Q2 is positive again. So Q3 is positive charge and minus Q1 equal to 0. Okay, because this plate has minus Q1, this has plus Q3, this has plus Q2. So the total charge for an isolated system will be 0. So that is what we had done here. Now I have got three equations and three unknown parameters. So I have this equation, I have this equation, and I have this equation. So I've got three equations. If I can solve it, and then we'll be able to find out the equivalent capacitance. Let us see how we can do this. I'll just write down the equations in the next page. Say I have, first of all, I have Q1 plus Q2 is equal to Q. Let it be equation number 1. Equation number 2, we have found out applying KVL, Q2 minus Q3 minus 2Q1, that is equal to 0. Again, we have got here Q2 plus Q3 minus Q1 to be 1, sorry, to be 0. This is from isolated system concept. So I can do one thing. From the last equation, I'll just find out Q1. So Q1 is equal to Q2 plus Q3. So this I can put in equation 2. If I put there, so I have already 3 Q2 minus Q3, and this is 2 of Q2 minus 2Q3. This is equal to 0. So look, I have then this is this. So minus Q2 minus 3Q3 is equal to 0. This will give you Q2 is equal to 3Q2. Sorry, Q3. 3Q3. So I have got Q2. So Q2 I have to write in terms of Q. I have to write in terms of Q. Okay. So how to do that? All right. First of all, let me find out Q to Q3. We have got a relationship anyway. So we can find out from here. So Q2 and Q3 has a relationship. So Q1 will be found out from here. So what we will get? So Q2 will write as 3 Q3, and Q3 is there. So this will be 4 Q3. Okay, again we have got a relationship between Q1 and Q3. Actually, we have to make use of this equation number 1 also. Better to, okay, let me just do one thing. Let me first go with the relay, because we have to ultimately get each of them Q1, Q2, Q3 in terms of Q. So better we'll just make use of this equation. So Q1 plus Q2, let me get Q1 from there. So Q1 from there means that will be Q1 is equal to Q minus Q2. Okay, Q minus Q2, and let me put here. Let me put here. Okay. Okay. So if we do that, then see Q2 plus Q3 is there, and this will be minus Q plus Q2. This is equal to 0. So this will give you 2Q2 plus Q3. That is equal to Q. So I have got a relationship between Q2 and Q3, right? So from here, I can just get one among them. Let me write Q3. Q3 is Q minus 2Q2. So this Q3 could be okay. Let us keep this. I think we should better find out what is Q1 and what is Q2. From here also, let me find out what is Q2. Q2. So this is Q minus Q3 divided by 2. And again, we have got this Q1. Let us just add this to Q1 plus Q2. This will be anyway Q, right? So Q1 is Q minus Q2, and Q2 is again, this is plus Q 3 by 2 equal to Q. So this will be 2Q. Oh, again Q2 has come. No, Q2 should not come. Anyway, I'll just give you now for the timing, I'll just give you the solution, and later we can just do once again how to find out this, like after solving this. After solving, okay, in the next class I'll just do the rigorous solving solution. Let me, for the timing, we'll just write down the solution. So we'll get actually from here Q1 is equal to 2 by 5 Q. Q2 will be 3 by 5 Q, and Q3 will be Q by 5 Q. So these are the values we should get. We'll just have to solve this three equations. From three equations, we have to solve and find out. Okay. All right. So once we get that, what we'll write? We'll write, see, between A and B, right? Between A and B, these are all between A and B. So VA minus VB, this will be is equal to total charge divided by equivalent capacitance, right? That is the total potential difference. So what is the total charge here? That is Q1 plus Q2. Okay, Q1 plus Q2. That is the total charge. Total charge. Okay, we have to write potential. Total potential will be, so potential difference between this thing. Okay, so look this here. Potential difference across anything. Okay, across these two, I'm just writing Q1 by C and Q2 by 2C. Okay, because at any branch, for any branch you just calculate, that will be V1 minus V2 because they are in parallel combination. So I'm writing Q1 by C, Q1 by C, and Q2 by 2C. Now I have got, so this I can write Q by C equivalent. So Q1 I have got 2 by 5Q. This will be obviously C here, plus Q2 I have got 3 by 5, 3 by 5 Q by 2C. Okay, let me get 1 over 5C common. Then what we get? 2Q plus 2 by 3Q, right? This is 7 by 2. So 7 by 10. 10 Q by C. Okay, so total Q by C. You can see that this is Q by C. So QQ can get cancelled from both sides. So this Q and this Q are the same. So we can get from here 1 over C equivalent is equal to 7C by 10, or I'm sorry, here C is in the down actually. Okay, with this 10C. Okay, this 7 by 10C. Okay, 7 by 10C. So C equivalent will be 10C by 7. So this is actually the answer. Okay, so I hope you have understood this. This is more general method to solve any kind of combination of capacitors. So it is a little bit tricky and lengthy also, but this will give you the correct answer if you can do it properly. Okay, so we'll stop it here for today. Next day we'll do the calculation, and next day basically we'll be learning CR circuit. CR circuit, charging of capacitor and discharging of capacitor through CR or through R. Okay. Okay, this can be switch on and switch off. Okay, so this is C and this is R. So next day we'll be learning CR circuit. CR circuit, charging and discharging of capacitors and discharging of capacitor. Of a capacitor. Okay, all right, so thank you for your patience. Bye for today.